Problem solving session, which is going to go and discuss the problems related to the material we covered over possible lectures. So, go ahead.
Quick question in regards to the videos. I just opened it up and it says University of Michigan that has a whole bunch of different.
Yeah, you have to log in with your Trax account,
Okay.
and then find this class, and then there will be a whole bunch of videos.
I got it.
You got it?
Yes.
All right.
Okay. Thanks.
All right. So which problem are you talking about? 2.2. Which part? 2.2 part 3. It says determine the Fourier series expansion for the following signals. Okay, so part 3, it's x 3 of t is going to be given as e to the t minus n for n t smaller than n plus 1. So what is the issue here? You don't know how to draw this. All right, so let's see if we can. How do we do this? This is t, so this is 0, 1, 2, 3, and so on. So in this interval here, when n is equal to n is between 0 and 1, so n is equal to 0, this is e to the t. So it's it looks like this, right? Okay. Then in this interval here, so this is n equals 0, this is e to the t. When n is equal to 1, then this is equal to e to the t minus 1. So how does e to the t minus 1 look like? Well, it's the same as e to the t, so it looks like this. Right? You follow? Yeah. So it is now periodic waveform that looks like this. That's it. So you can see what is the period. So this is n equal 2, n equal 3, and so on. Yeah, so just understanding this notation here, and that's going to be quite a I would say often, but sometimes you would these problems are not going to be the cleanest in the formulation. So you just come and ask, and I'll explain to you what the author meant. Any other questions from the board?
Also 6.
6. So that's 3. Let's look at 6. 6 was okay. 6 is a good problem. We're going to talk about something like that today. X6 of t is equal to sum when n goes from minus infinity to plus infinity, minus 1 to the n, delta of t minus n t. So the best thing to do here is to expand this a little bit, right? So let's just look at it for positive. It will give us an idea here. When n is equal to 0, this is minus 1 to 0 is 1, delta of t. So it's delta of t. When n is equal to 1, this becomes minus delta of t minus t, and then plus delta of t minus 2t, and so on. Okay? So the way you should see this is an alternating pulse train. If I were to draw this is how this would look like. This is t, this is, right, so this is 0, this is t capital, 2t, 3t, and so on. Here I have minus 1, minus 2, etc. So at 0, I have a delta pulse that is positive. At t, I have a delta pulse that's negative. At 2t, I have a delta pulse that's positive, 3t, and so on. So an interesting question to ask here is how large is the period? What's the period in this case? So this is the signal x6 of t. So what is the period here? What is the period in this case? 2t. So be careful, even though it's t capital, it doesn't have to be always t. The period is 2t. Okay? Any other questions?
How did you find the period is 2t?
Just look at it. I mean, this is after it which repeats, right? Right?
But can you find it how to find the graph from the function itself?
What like a formal way?
Uh-huh.
Well, let's call P0 here. Then following has to hold. F of t plus f is equal to f of t plus n t0, right? For every n. Right? So that's the definition of being periodic. So once you have a drawing of the function, that's always the best way. You draw the function first, and then you say, okay, how much do I shift this function to the left or to the right before it becomes itself? And you can see here that you need to shift this over here, and then everything shifts. So that's the best way of doing it. But it's always, regardless what you're doing, these problems, it is extremely beneficial to always draw, right? Make sure that use your calculator or use your knowledge of calculus, or just to draw the function. Once you draw the function, a lot of things come out really straight. Like, let's look at this guy here. What's the DC value?
0.
Right? So here, DC component A0 is equal to 0. What's the symmetry of this waveform? Is it odd or even?
Oh, this is
Is it what kind of symmetry it has? Even symmetry. So this is an even function. So as a result of that, Bn is going to be equal to 0 for every n. So the only thing that I need to calculate is an. So let's just calculate it. It's going to be really quick. So I'm going to integrate. You have to integrate in one period. So I'm going to integrate from 0 minus, right before this 0, to 2t minus, right here. Okay? To capture what is happening. So let's just write it. An is going to be 2 over period. Let me just say t0. Integral over the period, f of t, so x6 of t, times cosine 2 pi n f0 t. Here, f0 is equal to 1 over 2t, right? 1 over period. Okay, because the period is 2t. So let's just integrate this. An is going to be 2 over 2t, integral from 0 minus to 2t minus of delta of t minus delta of t minus 1 times cosine, oh sorry, not t minus 1, but rather t minus capital T. It's going to be cosine of 2 pi times n. Instead of f0, I can write 1 over 2t t. So far so good? This is just integrating one period and then substituting the value of the function as I find it over that particular period. There's nothing easier than integrating delta functions. It essentially just samples the value of the function at that point. So this becomes 1 over t, and then integral from 0 minus to 0 plus delta of t cosine just gives me 1. Because the value of the cosine at 0 is equal to 1. There's t here, right? You see? And then minus cosine 2 pi n times capital T over 2t. That's it. That's the integral. So let's just tidy this up a little bit. This becomes 1 over t. 1 minus cosine 2 and 2 cancels, and I have n. So my Fourier series in this case, x6 of t, is going to be 0 for the DC component. And then I'm just going to have summation when n goes from 1 to infinity, an, which is 1 over t, 1 minus cosine and pi, and then cosine 2 pi n over 1 over 2t times t. So that's my Fourier series of this waveform. Right? A lot of times in the books they try to, make this even look fancier. You can realize that cosine of n pi alternates. For n odd it is -1. For n even it is equal to 1. Right? Generally, what we know is this identity: cosine of n pi is equal -1 to the n. Right? You can check it. When n is equal to 0, cosine of 0 is 1, -1 to 0 is 1. When n is equal to 1, cosine of pi is -1, -1, and so on. Right? So it is true. So if I bring this back in, you can say x6 of t is sum when n goes from 1 to infinity, 1 over t, 1 minus -1 to the n, times cosine 2 pi. Let me cancel the 2 and 2. So it becomes pi and t over capital T. And now if you stare at this for a little bit longer time, you can see that the only ones that count are ones where n is even, n is odd, right? When n is odd, let's say for n equal to 2, 4, 6, and so on, you can see that this becomes equal to,
That's a good idea.
when n is equal, n is odd, then this becomes, so for 1, 3, 5, and so on, -1 to the odd number is -1, 1 minus -1 is 2. So alternative way to write this would be x6 of t is equal sum, let me say k goes from 1 to infinity, and then I can say 2 over t times cosine pi times 2k minus 1 t over capital T. Right, so that's a simplified version of it, because I'm just eliminating n's which are even, and I'm kind of making just the terms, all terms here. Right? So you can see here, when k is equal to 1, this is 1. When k is equal to 2, this is 3, and so on. So that's the Fourier series. Now, do you have to do this step? No. It's nice mathematically, but really, as soon as you get it here, you're fine, right? From here, I trust that you can evaluate this. If it happens to be 0, it's 0, right? And it's also valid information. If some coefficients are 0, that means I don't have any component at that particular frequency, right? Go ahead.
Yeah, if you were to graph that, I would imagine you wouldn't see it starting from n equals 1. It couldn't go all the way out to n equals -infinity to positive infinity.
No. Remember, this is a form 1. Remember form 1. X of t in general is a 0 plus sum when n goes from 1 to infinity. Right? An cosine 2 pi n f0t plus bn sine 2 pi n f0t, right? And we kind of calculated only an because we discounted this one on a basis that this function has a 0 mean, right? You can see as much as it is up, that's as much as is down, right? However much you have up, this much you have down. So on average, the function has a 0 DC. So that's the first thing that we concluded. And we discounted all the
these because the function hasn't been seen. So we kind of said, well, I don't need to calculate, so the only ones we calculate A's. And it turns out not all A's matter either. Only the ones for which n is odd, these are the ones that participate in this way.
Another question about that. When it starts out, the x of t, it starts the summation off from negative infinity to positive.
X of t, right? That's x of t. But that's this guy, right?
Yes.
Yeah, so, but this is over time, right? The summation is over time. Here, the summation is over frequency components, right? The other one is kind of summation over time. You have all of these delta pulses that are shifted in time.
Oh, I think your goal is to prove that it's periodic and then start from the form one because it's should be.
No, it is. I know it's periodic, right? I can see that just drawing here. I see it's periodic, and we determine its period, and that's where it kicks in. You know, as soon as the signal is periodic, the way I see it immediately is Fourier series. That's like a, Pavlov's dog. That's a response, right? You get periodic Fourier series, right? Just the immediate response, right? Because we, as I said, we see the world through harmonic analysis. That's just the way we see it. And when you're presented with periodic signal, all that you see is a bunch of sinusoidals, right?
So, I think sometimes you're going to give us like the even function. If we got like a even, I think it's going to be, it's very complex. Can we get example like this? Or?
Like this one? Is this
yeah,
complex?
but no, this is it's even. Okay, that's mean we can eliminate Bn. Okay,
Well, can we get a
starting
function
from
where-
0, we're going to eliminate A0, but
What happens if the function is neither?
Yeah.
Is that what you're saying? Well, what is complicated? Let's see, what does complicated
it's
mean?
going to be very long and that's
It
not-
just means I have a lot of integration to do, right? This is not complicated. As a process, integration is the most stable and best out of all of numerical processes. Numerically, it is much more stable to integrate than to differentiate. Differentiate, even small noise amplifies. So the question is now, okay, well, what happens on the exam, right? Well, on the exam, we pick the problems that are not tedious. Remember, I always do a test. It needs to fit within the 15 minutes. So that means, and I want to also test your understanding of 0 DC, what impact it has on the coefficient, your understanding of symmetry and so on. So on exams, you're likely to get a symmetry, right, of some sort. In real life, it's just a little bit more time, right? Come to work a little bit late, so they can finish it in time. Right? But Fourier series is really, really easy. And what happens is, I used to, when I went through this, that was for the first time maybe. It was like in 89, that time frame. And I bought a calculator and it had a numerical integration already in it, right? And I assume the progress has been made since those days. So every one of your calculators has a numerical integral. And I'm not saying always integrate numerically, because that's not the point here. But the point is, once I get the result, I can always punch in and see if I get within a couple of digits of accuracy. And if I get it, I just move on. Right? The problem is not hard, it's tedious, right? That's what the difficulty arises. And how do I do it and not make mistakes? And in all my years of first going to school and then teaching, there's no substitute like doing problems. Unfortunately, you have to just do 20, 30 problems, and then 21st or 31st becomes easier. That's the, go ahead.
On the definition of the impulse function, when t is equal to 0 should be infinity.
Correct.
But at this point, why you get it equal to 1?
Because I'm not looking at the value of the function, I'm looking at integral under the function. There is something called sifting property of the, property of delta function. Just for us who are not English speaking, coming from English speaking background, Sifting is, you know, when you put flour and you sift, and then, you know, the flour goes through and whatever are the larger particles, they surface, right? So that's sifting, so that's a sift. So let's take, what does this property say? It says if I integrate from, let's say, minus infinity to plus infinity, delta of t minus some tau, let me just not put tau because it may associate you with convolution. So delta minus some time t0, any function of f of t, dt. So this is what we're going to consider. Now, what do I know about the delta functions? It's 0 everywhere except at the point t0, right? So I'm going to actually say that this is equivalent when t goes from t0 minus to t0 plus, just integrating in a boundary around this t0. So I still have here delta of t minus t0 times f of t dt. Most of the time, f of t is a continuous function. So if I look at this function in an interval from t0 minus to t0 plus, what does this function become? It becomes a constant, right? It becomes the value of the function at f of t0, right? It's just one number because the interval is so small, the function has no time to change, right? So I can now treat this as a constant and take it outside of the integral, right? And this becomes f of t0, and then I have times the integral when t goes from t0 minus to t0 plus delta of t minus t0 dt. What's the value of this integral? This is area under the delta function, so this is 1. So this is f of t0. That's why I said earlier, integration with delta function is the simplest kind of integration. There's nothing really to integrate. All you do is find out the value of this function at whatever is the point at which delta becomes 0. So let's test this against here. I have two deltas. I have one at 0 and one at t. What is the value of this function at 0? 1. So this is this. What is the value of this function at t? 2 pi n times t over 2t. Right? And then it falls. So this is an important property. Note it. I mean, we use it all the time. It's actually the same thing. When I convolve with delta function, I get my function back. Okay? Any other questions? Let me go through, I have a whole bunch of problems that I'm going to also post, so this will give you also some additional material. Now this one is the one you're talking about, right? This one, that's why I kind of didn't do it. But that is tedious, right? You have this function that you need to integrate, right? And it has a BC value and it doesn't have any kind of symmetry, so it will have A's and B's and A0. Maybe I should have done that. If we have time in the end, I'll do it because I want to actually go and on this one. There's another one, very similar, and I wanted to do this one because it was a part of the proof of the sampling theorem, but I kind of skipped it. I say, if you go to the table 2.1, you're going to get this result. Let's use this as an opportunity to kind of shed the light, and in light of what we just went through, this should be an easy one. So the problem one, it says, consider a signal, x of t is equal to sum, when n goes from minus infinity to plus infinity, delta of t minus n t. Just to address a little bit what Jason asked earlier, let's expand this, get an idea, what is it that we're really summing here? So let's substitute n equal minus 1. So this becomes delta, there are some terms before, right? Before minus 1, but let's just start with minus 1. So delta of t plus 1, right? And then for n equals 0, this becomes delta of t. And for n equal 1, this is delta of t minus 1 t. Oh, sorry, t here.
and then plus delta of t minus 2t, and so on, right? So what is it that we're summing? We're summing all of these delta pulses that are shifted in time, right? So if I were to draw this waveform, here's my axis t. I'm going to call this x of t, and I'm going to deliberately call it also delta of t, because if you flip your notebook pages and look at how we call this when we was sampling theorem time, we call this delta of t sampling function. So how does this one look like? Well, it's a whole bunch of delta pulses that are spaced in the time domain by the interval t, capital T. So this is a 0, this is a minus t, minus 2t, and so on. Okay? So this is my sampling function. So let's derive all three forms. Let's just go through all three forms of a Fourier series. So how do we start? Let's start with the form 1. And my advice is always write them out. Just writing out the equations helps you calibrate and see what is important. So I always, even to this day, when I'm faced with these problems, I never go into the problem. First I write what do I need to calculate. So I'm going to express x of t as a0 plus sum when n goes from 1 to infinity, an cosine 2 pi n f0t plus bn sine 2 pi n f0t. What is f0 in this case?
Here.
F0 is what? 1 over t. 1 over t, right? The period of this one is t. How do I see that? If I shift it by t, it becomes itself. So now, I look at this and say, okay, there's a0, there's an and bn that I need to calculate. So how am I going to integrate? This takes a little practice. What I'm going to do is I'm going to integrate it from minus t over 2 to t over 2. That is going to be the period that I integrate, right? From here to here. Okay? So, what is a0? 1 over t. Do we all see that that's the case? Right? That's the first thing. You guess, and then you demonstrate that this is the case. How do you guess it? Well, if I integrate from here to here, essentially I'm integrating the area under this delta, which is 1, and I have to divide by the duration of the integration interval, which is 1 over t, to get the answer. But formally, this is 1 over t, integral over t, x of t, dt, and then I reduce this to 1 over t, integral from minus t over 2 to t over 2, delta over t dt, which is 1 over t. So I have calculated a0, I guessed it, I calculated, so I'm reasonably happy that what I have here is correct. Now, what is the symmetry that this function possesses? Even function, right? How do I see it's even? If I flip it, I get back the same thing. So because the function is even, I can conclude that Bn is going to be equal to 0 for every n. So therefore, I don't need waste any time calculating Bn. So I need to do is calculate An. And An, the formula is 2 over t, integral over t, x of t, times cosine 2 pi n f0 t dt. That's the formula. In my case here, this becomes 2 over t, integral from 0 minus to 0 plus, right? Because I'm just integrating delta function. So it's going to be delta of t times cosine 2 pi and f0 t dt. Now, what's the value of this integral? Look at the sifting property. It is 1. Why is it 1? Because what matters is only the value of this function at the point where delta is non-zero. And otherwise, in this point 0, the value of this function cosine is 1. So the value of this integral is 2 over t. So very quickly, I get that my x of t in a form 1 is 1 over t plus 2 over t sum when n goes from from 1 to infinity, cosine 2 pi n over, I can say capital T times T. So that's my Fourier series associated with this waveform. What's interesting about this one is that it has all harmonics. They're all of the same magnitude, right? They never decrease, right? They're always having the magnitude 2 over T. So to build this waveform, I need an infinite band, right? Because I need all the cosines of an integer multiple of the fundamental frequency all the way to infinity, right? So that is telling you that this is not the reality, and it's in every practical scenario we're going to have something that approximates this. Okay? All right, so that's the form 1. And it has, as I said, this one is always the one that this me, or this I try to calculate this one first. Then let's take a look at form 2. Sure.
Just a quick question. You did 0 negative, 0 positive because you're analyzing the delta function at
Yeah.
dt. You also analyzed delta function at dt, but you did it outside of that range of negative t or 2 to
Yeah,
positive.
but this is moot point, right? Integrating over this gives you nothing, because delta is 0 there anyway. So this integral, I just left it. There's maybe one more step that I could have inserted here. 0 minus to 0 plus in terms of t dt, right? Because this integral here, these boundaries, they just collapse to 0 minus 0 plus. Because outside of that interval, delta is 0 anyway. Right? And there's nothing to integrate.
I have one more question. Is the rule of thumb is to integrate between the halfway point between the 2 periods? Is that what
No,
it
you
is?
gotta. That's where the experience comes in. Sometimes you're gonna integrate between minus and plus. Minus t over 2 to t over 2. You tend to integrate over that interval whenever you try to exploit the symmetry of the waveform, right? So if it has even or odd symmetry, then you are integrating in these boundaries. Most of the time, that's going to be the case. But ultimately, it's just one of the choices you make. And the theory says, and the practice also, is that even if you chose different interval, you're going to get the same result. Choice of the interval is not going to impact the accuracy, the accuracy of your result. You're not going to do anything wrong. It may give you more or less work, depending on just how the waveform is.
So negative t over 4 to plus t over 4 would be the exact
No. Negative t over 4 to 3 t over 4.
Oh.
You have to integrate over the entire
Oh, I see.
period of t.
I see,
you know,
I see.
Okay. So from 0 to t sometimes, from minus t over 4 to 3 t over 4 is valid. From 0 minus to 2t minus. Remember the first example I did. Just from 0 minus to t minus, sorry, if t is the period. So you can do any interval as long as it's t length of it. But the choice where you start and where you end, it might depend on the actual waveform. And that comes with experience. All right, so let's, this is form 1. Let's do other forms too, so we get an idea. So form 2. And again, you write it up. X of t is c0 plus sum when n goes from 1 to infinity, cn cosine 2 pi n of 0t plus theta n. Now this one doesn't have its own calculation formulas, but we are already determined the form 1. So here is just a matter of mapping. C0 is the same as A0. Cn is going to be square root of an squared plus bn squared. Well, it's whatever is the magnitude of an. And you can see here the magnitude of an. An is always positive. So the Cn is going to be 2 over t.
And theta n is going to be arctangent of Bn over An. In this case, An is always positive, so this theta n is always going to be equal to 0. So the form 2 and the form 1 in this particular case are the same. So it's 1 over t plus 2 over t sum when n goes from 1 through infinity, An cosine 2 pi n 1 over t times t. So that's the form 2 for this, this waveform. Form 3. Form 3 is the complex Fourier series. In form 3, we say x of t is sum when n goes from minus infinity to plus infinity, xn e to the j 2 pi n f0 t. Now xn has a calculation formula. It is 1 over t integral over t x of t e to the minus j 2 pi n f0 t dt. So this is how x of t needs to be xn needs to be calculated. So in this particular case, xn becomes 1 over t integral from minus t over 2 to t over 2 delta of t times e to the minus j 2 pi n f0 t dt. Now, what is the value of this integral? Delta will sample this function at 0. What's the value of this function when t is equal to 0?
1.
1. So this is just 1 over t. And our Fourier series, x of t is going to be sum when n goes from minus infinity to plus infinity, 1 over t e to the plus j 2 pi n f0 t. So that's a Fourier series. And then a final check. Always do this check when it comes to complex Fourier. You're going to say, what happens when n is equal to 0? So what is x0? What's the value of x0? Substitute here. Where is xn? Xn is this. So what is the value of xn when n is equal to 0?
It's infinity.
No.
1 over.
Yes, for every n. So it's 1 over t even when n is equal to 0. Now, what is the physical meaning of x0? DC component. So is the DC of that waveform equal 1 over t? Yes. So I just kind of closed the loop. Right? Because I didn't use that anywhere in derivation, but I got to the end, I substituted n equals 0. It turned out to be what I knew that it needs to be from the very beginning. So I'm kind of confident that this integral is correct. Okay? A lot of times you're not going to be able to guess the DC value, but you're going to look at what you get here, and you're going to ballpark it. You know, if it turns out to be 753, and the waveform gives you one is between 0 and 2, you know that the average is somewhere between 0 and 2. It cannot be 753. So you got to go back and look at the integral. All right? Let me do the next one. Okay, so now let's look at this problem. Consider two signals. The first signal is our friend, delta of t, which is sum when n goes from minus infinity to plus infinity, delta of t minus nt. This is our periodic pulse train, impulse train, I should say, and that's the one that we've been dealing so far. And the other one is some signal x of t that has a Fourier transform x of f. So some arbitrary signal. I'm not putting any restriction on this signal except that it has a Fourier transform. Go ahead.
Yeah, and We'll go back to form 2. There is an, the last step in form 2, there is, I think, no and before the
There is a minus here.
the-
That's done.
I'm talking about the and.
AN here?
No, the last one, the last step, yeah. Yeah, this one is correct.
Oh. Okay. So we have delta of t, and we have an arbitrary signal x of t on which I'm not putting any restrictions except that it has a Fourier transform, right? That this exists. Now the question is find out Fourier transform of x of t times delta of t. And this is essentially saying find the Fourier transform of the product of those two, which is essentially find the Fourier transform of the sampled signal. Because I know what happens when I multiply this and this. I'm sampling my signal, right? Last time when we worked the sampling theorem, we said, well, we had one other sub-theorem that said that Fourier transform of the product is the convolution of the Fourier transforms, and we solved it that way. But here, I have already decomposed this delta of t into Fourier series, so let me use that. Go ahead. Going back to
For,
the...
yes,
Uh-huh.
another one. You said the convert between the form 1 and form t is
Oh.
convert between form 1 and form t xn equal to an minus jbn over 2.
Yes.
And in this case, n is equal to minus infinity to plus infinity.
Yes.
And this case is equal to 1.
Correct. So an, let's just, you remember we had the formulas a minus n is equal to an, and b minus n is equal to minus en. Those were the two formulas that we demonstrated last time, right? One of the results. So let's test here. I have xn, the general formula is an minus jbn over 2. Maybe this one is not the best one to test, but because here, if I substitute, an was 2 over t minus j0 over 2, which is 1 over t for every n, right? And that is true, right? But maybe if we do some other problems, we test this. But remember these two relationships. That's this is what we demonstrated last time, right? So if you go to minus x minus 3, it's going to be a3. B minus 3 is going to be minus b of 3, right? And then the formula holds.
I'm sorry, what allows me to take the Fourier transform of the two signals instead of just doing it for x?
Okay, well let's are we done with this one? Let's move here. So let me remember, refresh what we were doing here. We have two signals. One is delta, which is the impulse train, and the other one is an arbitrary signal for which I have a Fourier transform. And the question is, find the Fourier transform of the product of the two. This is a practical problem, right? The translation of what the math here says is, find the Fourier transform of the sampled signal, right? So, and last time I said we did that using the convolution in frequency domain, but here we're going to actually do it slightly different. I'm going to say this is a Fourier transform of x of t, and then look, instead of this delta of t, I'm going to substitute its Fourier series. Right? This is what we just, I'm using form 1. This is what we just derived. Now, Fourier transform is a linear transform. So this, I can actually say the Fourier transform of the sum is the sum of the Fourier transforms. So this becomes Fourier transform. Let me take this first term, 1 over t x of t, and then plus sum when n goes from 1 to infinity, 2 over t
times the Fourier transform of x of t times cosine 2 pi n L0 t. Now, the first one is easy, right? Because Fourier transform of this constant comes outside, and this is just 1 over t times x of f, right? So this is 1 over t times x of f. And then plus sum, when n goes from 1 to infinity. Now, what is the Fourier transform of x of t times cosine? We use the modulation property of the Fourier transform. And we know that this is 2 over t times 1/2 x of f plus n f0 and plus x of f minus n f0. We proved this last time. We call this modulation property of the Fourier transform, saying that the Fourier transform of the signal multiplied with the cosine, actually this multiplication translates the spectrum of the signal from the baseband to the portion of the spectrum that's centered around the carrier frequency. Now, if you look at this, 2 and 2 will cancel, so I have 1 over t as a common. So this Fourier transform of x of t multiplying delta of t is equal to 1 over t times x of f plus 1 over t sum when n goes from from 1 to infinity x of f minus n f0 and plus 1 over t sum when n goes from 1 to infinity x of f plus n f0. Right? So I have, what did I do? I took this one summation and broke it into 2. Right? And now I'm going to rewrite this in a special way. I'm going to take this one here, and instead of summing from 1 to infinity, I'm going to sum from minus infinity to minus 1. So I'm going to say the first one here is going to be 1 over t sum when n goes from minus infinity to minus 1 x of f minus n f0. Why? Because, since I'm now inverting the sign here, I have to invert the sign here. Then I'm going to write this one in a special way. It's going to be 1 over t sum, or I shouldn't put sum, I'm just going to put x of f minus 0 times f0. And then the last one I'm going to write sum when n goes from 1 to infinity, x of f minus n f0. So look at these three. They're identical, right? In terms of the sum argument. What is it that I'm summing here, right? I'm always summing x of f minus n f0. It's just the different boundaries. Here I go from minus infinity to minus 1. Then at 0 I have this one. Then I continue from 1 to infinity. So all three of them can be actually written as 1 over t sum when n goes from minus infinity to plus infinity x of f minus n f0. Okay? And that's the result that we had from the last time. We said that the sampling in the time domain performs the periodic extension of the spectrum of the signal in the frequency domain. Remember? Let me draw this as a because I want you to remember this picture, right? So here's where we start. We said this is my x of f, and then I look at this as now frequency axis. This is in time in frequency axis too. So this is f as well. Let's say this is 0. This is f0, 2f0, 3f0, minus f0, minus 2f0, and so on. So if I were to draw this waveform, this is a Fourier transform of x of t times delta of t. You have your signal back here, let's say this guy, at 0. And then you take the spectrum and you start repeating it along the f-axis. So you have another one here,
another one here, another one here, and so on. So if you look at the aggregate of this, you end up with something that might look somewhat like this, right? This is the overall spectrum that comes as a periodic extension. I draw it deliberately here, this way, to tell you that this is true always. I didn't have to assume anything in terms of the relationship between sampling interval and the highest frequency in the spectrum of this signal, right? And this always holds. In a special case, when my sampling frequency is high enough so that these guys are separated in the frequency domain, I can reconstruct my signal back through low-pass filtering of this baseband component here. But in other cases, this formula is true as well, except that because of the overlap of the spectrum in the frequency domain, I cannot reconstruct the signal back. And that was one of the big assumptions behind the sampling theorem, that your sampling frequency is larger than twice the largest frequency in the content of the signal. But that's not because this formula is not true, but it's because if you want to reconstruct it, you cannot have the mixing of the frequency domain. Okay? Any questions here? Okay. I'll just look at the next problem. So the next problem considers two signals. One is signal x of t and y of t, and they're both periodic with period t0. And it says let xn and yn be the coefficients of their Fourier series. Fourier series coefficients. It says show that 1 over t0, integral over t0, x of t times y, complex conjugate of t dt is equal to sum when n goes from minus infinity to plus infinity, xn, yn, complex conjugate. Fourier coefficients here, maybe I should put form 3 so that we know that it's a complex Fourier series. Now, the way I'm going to do this is, let me just exercise the formulas as we learn them, and then I'll just mention it, and we're going to actually spend a lot of time on this later, of what does this actually represent, because this has a special meaning to us, this particular form. So let's just do what we already kind of know. X of t is a periodic with these coefficients xn, so I can say x of t is sum when n goes from minus infinity to plus infinity, xn e to the minus plus j 2 pi n f0 t, where this f0 is the fundamental frequency 1 over t0. This is just saying that x of t can be expressed as a complex Fourier series, which is true by the virtue that it's periodic. Now y of t is the same thing. It's the sum, let's say n goes from minus infinity to plus infinity, xm e to the j 2 pi n f0 t. Right? So that's my y of t. It's also periodic, except that this needs to be y, right? Not x, right? Y, n. Okay. So now let's take these two, put them in this integral here, and see what happens. So once I do the substitution, here's what I have. 1 over t0, integral over t0, x of t times y complex conjugate of t dt becomes an integral 1 over t0, integral with t goes just over t0. And then here first sum.
n goes from minus infinity to plus infinity, xn e to the j 2 pi n f0 t. So that's my first integral. The second integral is sum when n goes from minus infinity to plus infinity, yn e to the j 2 pi m f0 t, and then I put complex conjugate here, and then I integrate over t. So that's just a straightforward substitution. And like all the problems, I keep on saying that whenever the things get complicated in communications, you swap the order of integration and summation, and they tend to simplify. So here I'm going to do this. It's going to be sum. N goes from minus infinity to plus infinity. Sum. N goes from minus infinity to plus infinity. Let's put here whatever doesn't require any t, right? Because I'm going to just take out whatever is not having t. So it's going to be xn times yn, but because of this complex conjugate here, I have to complex conjugate yn. And then what I'm left with is this integral, 1 over t0, integral over t0, e to the j 2 pi n minus m f0 t dt. Okay? Where is this minus coming from? From the complex conjugate, right? Complex conjugate of the exponentials, which is the sign over at the exponential. So this integral here is the one that we need to consider. So let me call this I. So we have two cases. First case, n is different than n. Right? I have a case where these two numbers are different. So this integral I becomes 1 over t0, integral t0, and I'm just going to use the Euler's identity here. So this becomes cosine 2 pi n minus mt plus j sine of 2 pi n minus m f0 t. I guess f0 needs to be inserted here as well. dt. What's the value of this integral? Well, let's look at it. What does it actually do? The period, if n minus m is equal to 1, so they're right next to each other, right? Then you have 2 pi f0 t. What's the period of that one? It's 1 over f0, right? It's t0. Cosine 2 pi f0 t. What's the period?
0.
Period cannot be 0. 2 pi f0 t. What's the period there?
T over 2.
1 over f0, right? If you have a cosine, let me just write a cosine 2 pi f0 t, then period is what? 1 over f0, right? 1 over this. 2 pi over omega. This is omega, right? So the period, this is frequency. The period is 1 over frequency. So if you look at what is happening here, and what I have here, I have a cosine that has a period at least t0. It can be smaller than t0. If n minus m is greater than 1, then the period is smaller than t0. But whatever may be the case, I'm integrating the cosine over integer number of its periods. So what is the value of that integral? What's the value of that integral? Look, I have a cosine, right? And I'm integrating over, let's say, 1 period. So what's the value of the integral? What's the area under the curve? 0. Integrating periodic function, cosine actually, not periodic, integrating cosine or sine over integer number of periods is 0. So this is 0. How about this one? When n is different than m. I'm integrating again sine over the integer number of periods. Same. That's the same thing, right? Sine and cosine are the same functions, just shifted a little bit in time, right? Shifted by quarter of a period of time. But here I'm integrating over integer number of full periods. So to make long story short, this thing is 0, right? Always. Now, in an interesting case is when n is equal to m. In that case, my integral I becomes 1 over t0, integral over t0. When n is equal to m, this is 0, e to the j0 is 1 dt. So what's the value of this? 1. Right? Because integral over this is t. Substituted from 0 to t0. So the value here is 1. I'm taking an average of 1. Right? So average of constant into constant itself. So now that I have the value for n equal m, so this integral only is non-zero when n is equal to m. So it appears that I'm having a double summation here, but I'm not. Every time n is different than m, this integral kills it, right? And whenever n is equal to m, this integral gives it 1. So this whole thing here, so 1 over t0, integral over t0, x of t times y complex conjugate of t dt becomes summation when n is equal to minus infinity to plus infinity, xn, and then yn complex conjugate. Okay, and that's it, right? That's what was to be proved. This form here has a special meaning to us. We turns out this is dot product between two functions, right? This is how we take what we call inner product. Right? And what you kind of already know that analogy. Let me just refresh your memory. You know, let's say we're dealing with vectors, right? We take the vector, you take the magnitude of the first one, magnitude of the second one, times the cosine of the angle between them. So that's the geometrical interpretation, right? And this is equivalent to this. But you also know, if I express the vectors in terms of their coordinates, then I can take the dot product as the sum of the inner products between them, right? And that's the same thing here. We're going to be doing a lot of this when we start doing digital communication, because it turns out the way how you receive the signals, you take the dot product with whatever it is that you're receiving against the known basis functions to determine which one was actually sent.
Isn't it true that for you to convert from n to m, what allows you to do that is n is equal to n minus 1?
No. I'm having this double summation. I'm not converting from anything to anything.
They're just representing two values.
Maybe the confusing, the nature of the question, I think, is this. Why did I write here n goes from minus infinity, and why did I write here m goes to minus infinity, right? It doesn't matter. I could have chosen any letter, because this is just a dummy variable that sums from. But I did this deliberately because I wanted to put it in here. And I want to indicate that essentially what this appears to be is this, right? Let's say this is n, and this is n. So you have here x0, x1, x2, and so on, x minus 1, and so on, y minus 1, y0, y1, y2, and so on. So you think of this as what essentially this summation is an infinite matrix, right? Where at every point here you have xi, j, xi times yj complex conjugate, right? And if I were to look at just this section here, it seems like I need to sum over the entire table. But then this integral adds the twist to it. It says wherever you are off main diagonal, the value of this integral is 0. And whenever you are on the diagonal, the value of the integral is 1. So really, even though I'm summing over this entire matrix, the only non-zero components are here on the main diagonal. So that's why this double summation collapses into a single summation. Okay. Any other questions? All right, so let me look at oh, this is different lecture. I have time for just one problem, so I'm trying to see which one should I do, right? Let me do this one, because even though it's a little bit more complicated, the other ones I hope you're going to find straightforward. If not, then ask next time, we're going to go over them as well. But this is problem 6, in this handout here, or these notes. So I have a linear time invariant system. And I have the impulse response of that system equal to e to the minus alpha t times u of t. U of t here is that step function that says this is e to the minus alpha t when t is greater than 0 and 0 otherwise. Okay? And then I have an input signal, x of t, which is equal to e to the minus beta t times u of t. And I have alpha different than beta. And the question here is, use the frequency domain analysis to find the output of the system, determine power and the energy of the output signal. I don't know if I determine power. So here's what we are dealing with here. That's, remember my story of two worlds? That's the exercise of that. Linear time invariant system is pretty much starting point for us modeling anything. So, you know, if nothing else is given, you try it as a linear. Even if it's not linear, you're always going to try it as linear and then discuss how the actual one is different than the ideal linear approximation. So, linear time invariant system can be characterized with h of t, which is an impulse response. This is what comes out of this system if it's hit by delta function. The Fourier transform of this guy, how do we call that? Frequency response. So h of t and h of f are Fourier transform pairs. If I put signal x of t, I'm going to get a signal y of t. What do I know about the relationship of x of t and y of t? Y of t can be determined as x of t convolved with h of t, right? So this is x of t convolved with, with h of t. And that's a time domain analysis. So this is our time domain. Alternative to the time domain, since I already have the frequency response, which is the Fourier transform of the impulse response, I can find x of f, which is going to be the transform of the input. And then I get y of f as x of f, and then what? Times h of t. In most cases, the taking multiplication is far easier than doing the convolution. So we prefer this representation here. So what the problem says here is, okay, I gave you the impulse response, I gave you this one, I gave you this one, but what I really want you to do is find this guy. Right? Find the y of f, and then if it needs to be, you can get back this y of t as an inverse Fourier transform. But a lot of times, really, what we really care about is this view in the frequency domain. This is what most of the time we're going to be concerned about. So how do I do that? Well, let's first determine the things that we need. H of f, x of f, sorry, is the Fourier transform of x of t. And this is a table one, so this is a Fourier transform of e to the minus alpha t, u of t. And this is, if memory serves me right, 1 over alpha plus j 2 pi f. That's the Fourier transform of x of f. Now, h of f is the Fourier transform of h of t, and this is Fourier transform of e to the minus beta t. Or what did I say? Oh, I did them the other way around. So this is beta, this is beta, and here it's alpha t, u of t, and we know that this is 1 over alpha plus j 2 pi f. So what is y of f? Is the product of these two. So it is equal to 1 over alpha plus j 2 pi f times 1 over beta plus j 2 pi f. And that's the end of the problem, right? See how easy it is in the frequency domain. Now, where it becomes tricky, you cannot trick the nature, right? You have to pay somewhere. It is the question where you need to pay, right? If I now really want to know y of t, I have to take the inverse Fourier transform of this guy. And in the complexity, that's pretty much the same complexity as doing the convolution. So if I need y of t, then I have to take the inverse Fourier transform of this, and I think I have enough time to do that here. A lot of times you're not gonna have to do it. You're gonna see whatever you need to see from the frequency domain representation. In what we are trying to do here, and this is in communication systems, 9 out of 10 times, the frequency domain view is going to be much more exciting. It's going to tell us way more than the time domain. But let's determine y of t, just to see if your memory serves you well. We need to determine inverse Fourier transform of this. How do I determine that? What I'm going to say here is I need to decompose this using first partial fraction expansion, and then take the Fourier transform of individual terms. Now, just to let's do this. Let's call j 2 pi f. Let's define it as s, so that we save some writing space. And then look at y 1 over alpha plus s times 1 over beta plus s. And I'm going to write this as a alpha plus s plus b beta plus s. Right? That's our partial fraction expansion. And when you sum these together, this becomes alpha plus s times beta plus s. And then I have here a plus b times s plus a beta plus b alpha. And then this needs to be equal to this. So from here I get that a plus b is equal to 0, and a beta plus b alpha is going to be equal to 1. And this one is very easy to solve. From here, you get that b needs to be minus a. If you put that in here, you get a, b, beta minus alpha is equal to 1. Therefore, a is equal to 1 over beta minus alpha. And obviously, b is going to be minus 1 over beta minus alpha. So now knowing that, I can put that back in here. So you end up with the So you end up y of f. Instead of a, I'm going to write 1 over beta minus alpha times what do I have? Alpha plus j 2 pi f. Alpha plus j 2 pi f. And then minus 1 over beta minus alpha, beta plus j 2 pi f. So if I take the inverse Fourier transform, y of t is going to be 1 over beta minus alpha, e to the minus alpha t minus e to the minus beta t, everything So that's the output of the system. Just I obtained it as an inverse Fourier transform here. This is a constant, falls outside. The inverse Fourier transform of 1 over alpha is j 2 pi f plus e to the minus alpha t times u of t, and then this is the inverse Fourier transform of this. But you know, this is what I guess in this case is relatively simple. But what is important is the path that we travel. As I said, most of the time we're going to actually be traveling this path, and every now and then, if we want to understand something in time domain, we might do the inverse Fourier transform. But you will see in this course we're going to actually almost all the time working in frequency. Go ahead.
Which identity did you use to go from YF to
Y of t is obviously Fourier inverse transform of y of x, right? And then I skipped quite a few steps here, but let's just put in 1 minus beta minus alpha times 1 over alpha plus j 2 pi f, and then plus, or rather minus 1 over beta minus alpha times 1 over beta plus j 2 pi f, right? So far so good, just substitute, right? Y of f is this. So now, this is constant, comes outside. So this is 1 over beta minus alpha, inverse Fourier transform of 1 over alpha plus j 2 pi f, and then minus 1 over beta minus alpha, inverse Fourier transform of 1 minus beta plus j 2 pi f. Now, this is a table entry, right? In table 2.1 you have this, and this is 1 over beta minus alpha e to the minus j alpha t, and then minus e to the minus j. No, it's just beta t, and then everything minus j. So then these are the steps that I kind of skip. Okay. Any questions? All right, there's a couple of more problems. I think maybe 3 more problems in these notes. So just go over them as well. And I'm going to stop now, give you 15-minute break, and then we come back and do the A and H.